We're going to make an amounts table. All right, so we have initial, change, final. We're going to go ahead and make a column in a row. Okay, so any questions so far? Taking initial grams, converting to moles, make an amounts table, and we're going to take these initial moles and we're going to put them into their appropriate boxes. What goes here is 0 because of the fact that the reaction hasn't started yet. Are you with me? All right, any questions so far? So just taking the initial moles, converting to grams, putting them in the table. Okay, from here, we have to figure out which one's limiting. Now, in the previous problem, let's show the way we did here. In this way, we just took the initial moles and divided it by the coefficients. I'm just not going to multiply through by 2 to get rid of the moles, right? I'm just going to take the initial moles, divided by the coefficients. Whichever one was smaller there tells me which one was limiting. Okay, so, but here's the thing, I'm not going to include those numbers in the table. All right, I'm just going to sort of use a sidebar here to figure that out. So I'm just going to say, okay, for aluminum, I'm going to take 2.780 initial moles, okay, divided by the 4, okay, and I end up getting 0.65. And then for the oxygen, I take the 6.250 initial moles and divide that by 3, and I get 2.08. And again, aluminum comes out smaller, not surprisingly, because it came out smaller over there too. Okay, so what this tells us is that Al is the limiting reactant. So what do we do with this information? So in terms of the amounts table, what it tells us is that we're going to end up with a final amount of 0 for aluminum. Now that's what that tells us. So if we're going to end up with a final amount of aluminum, that means we have to subtract all of it from the initial in this table. So I'm going to say minus 2.780 in my table. So 2.780 minus 2.780 equals my final amount of 0. So if it turned out that the oxygen came out lower, then I would be subtracting all of this 6.25 from the initial and ending up with 0 here. All right, that's what that tells us. Now here's the really cool thing. I can take this minus 2.780 and I can put that number in all the other boxes in that row. And for the reactants, we're still losing some reactants, so I'm going to put a minus sign for all the reactant columns. For all the product columns, since we're forming that product, we're gaining that. So I'm going to put a plus sign in front of the number for the columns for the products. So it's the same number. You just have to remember things turn positive when you have products because you're gaining that, you're forming it. Now here's where the stoichiometry comes in. for every mole of Al that I lose, how many moles of oxygen do I also lose? I lose 3 moles of oxygen for every 4 moles of aluminum that I lose. So in this case, it'll be 3 moles of O2 for every 4 moles of Al that I lose. So the stoichiometry happens in the table. All right, and it's a fraction. The reason why we have to do this is because to subtract moles of aluminum directly from moles of oxygen without taking into account the stoichiometry would not be accurate, right? We have to convert moles of aluminum into moles of oxygen lost, then subtract the moles of oxygen lost from the initial moles of oxygen that we started with. And that gives us a moles of oxygen that will be left down here. So taking 6.250 minus, bless you, so taking 6.250 minus this 2.78 times 3/4 will give us our initial, our final amount here for oxygen. All right, so that would come out to be 4.165 moles of oxygen left. So just to reiterate how this number came about, okay, let me write a different color here. So this number came from 6.250, okay, minus 2.780 times 3/4. All right, that's how I got that number. So you have to take the 2.780 times 3/4 and then subtract that whole result from the initial to get the final. Okay, and then we have our product side. And this is easy because it's just adding whatever was made to 0. Okay, so 0 plus this amount gives us our final amount. Now actually it's, oops, correction, okay. We'd have to take into account the stoichiometry here as well. So what should be my fraction here? Yeah, it's 2 moles of this produced for every 4 moles of aluminum lost. Right, so 2 moles of AlO2 produced for every 4 moles of Al lost. Notice how it's dividing by 4 every time. So with exception to the limiting reactant column, all the other fractions and all the other columns will always have a 4 in the denominator because it's all based on how much is lost of our limiting reactant. And the number in the numerator for these fractions will always be the coefficient above that column. Okay. So 2.78 times 2 over 4, that's going to give us 1.389 moles of Al2, O3 left. I'm sorry, produced. So it looks like we're like far from being done to getting to this point. We're actually really close. So notice how this is 3.89 here for moles of AlO2 produced. What do we have here? 1.39. So we just take the final moles from the table, multiply by the molar mass, and we'll get our answer. For the moles of oxygen left, it looks different, but we'll get the same answer. Okay. Okay, so theoretical yield for our product, 1.389 moles of O2 times the molar mass of that, which is 101.96. This is a brand new marker and it just doesn't look very bright. Anyway. Okay, so that comes out to be 142, just like we got before. Okay, mass of O2 left, really easy too. How do we do that? So if you look at that, it looks complicated. But if you just take the final moles from the table here, 4.165 moles of O2 times the molar mass of O2, which is 32 grams per mole. All right, and that would come out to be 133. And that's it. So you get the same answers as the 107 method, but it's more streamlined into a compact table. Any questions? We'll have to practice this in problem solving for sure, but that'll have to wait till next Friday, but anyway. All right, so just to summarize here. So get the grams, turn them into moles for the reactants, put them in the table, divide each one by the coefficient, look at which one is smaller of those two. After you see which one is smaller, you figure, okay, that one goes to 0. We don't use these numbers, we just use it to make a decision. It's like LeBron and the decision, right? Okay, if you don't remember the decision, never mind, but, okay. Back when he was a free agent, went to Miami, he had this, like, this television special, The Decision, because he's so important, he, you know, had to broadcast it. He is like Thanos in the comic book world, I have to admit. Okay. So, so we end up with 0, okay, and then we take that same number, put it in the other columns. Now, this is only 3 columns, right? What if we had a reaction that had 4 different reactants and 4 different products? Okay, and you can see how this method would probably help you streamline things a lot more easily versus a simpler reaction like this. Okay, so whatever's lost here goes in the other columns. For products, make sure it's a positive sign for the products. Okay, and then you got to use the stoichiometry, so it's 3 over 4. 3 divided by 4 goes here. 2 divided by 4 goes here. Okay, add that to whatever is 0 here, you get that. Subtract this amount from the initial moles to get the final amount. And then you've got your final moles. Once you've got your final moles, you're in the home stretch. It's just converting the moles back into grams or converting them back into molarity or converting it back into atmospheres, depending if it's a gas problem. All right, so next Friday, during problem solving,